Okay, 5.2 subspace. Definition: a subspace of W of a vector space V is called a subspace of V if vector W is itself a vector space with the same scalars addition and scalar multiplications as V. Okay, so if V is a subspace in W, then it should follow these two criteria, which is let V be a vector space and W is a non-empty set of V. Then W is a subspace of V. Okay, W is a subspace of V if and only if the following conditions hold. First condition, if U and V are in W, then U plus V also must be in W. This is the first condition. Second condition, if U is in W and C is scalar, then C U also is in W. Okay, if these two conditions are met, then we say W is a subspace of V. Okay, example. Okay, example. The point in a plane through the origin of R3 form a subspace of R3. Okay, R3 meaning that space in 3 dimension. Okay, let W be any plane through the origin and let U and V be any vector in W. So this is how we show that W is a subspace of R3. Okay, then U plus V must lie also in W. Okay, let W be any plane through the origin and let U and V be any vectors in W. Then U plus V also must lie in W because it is the diagonal of the parallelogram. Okay, determined by U and V. And also K is any scalar and K times the vector U also must lie in W for any scalar K because KU lies on a line through U. Okay, thus W is closed under addition and scalar multiplication, so it is a subspace of R3. Okay, now we have proved that W is a subspace of R3. Okay, let U and V be any vector in W. Okay, U, V, any vector in a W, where W is in R3, okay, in the plane R3. Okay, so now let's say this is U and this is V. Okay, so using addition of vector U plus V, so we have this one, UV. And still U plus V also in the R3 space. Okay, so that's why U plus V also lie in R3. Okay, so the first condition met. Okay, second condition, okay, this is U. Okay, let K be any scalar and KU means the extension of U. So we have this one. The extension of U also lies in the plane, in the R3 plane. Okay, so the second condition also met. U and V is in R3 and U plus V also lies in the R3. First condition met. The second condition, let K be any scalar and U is the vector in R3. So KU is, we extend the vector U. So we have KU here also lies in R3. So it met the second condition. So therefore, since UV is in W, U plus V also in W and KU also in W. So therefore, W is a subspace of R3. Okay, so another example. Okay, a subset of R2 is not a subspace. So why a subset of R2 is not a subspace? Okay, let W be set of any all points in XY in two dimension R2 such that X greater than 0 and Y also greater than 0. So these are the points in the first quadrant, okay, in R2. Okay, the set W is not a subspace of R2 since it is not closed under scalar multiplication. For example, let V is 1 in 1 lies in R2, which is in W, but it's negative. Negative 1V, negative 1V is negative V, being a component negative 1 is on the opposite side, not in R2. R2 only this part. Okay, R2 only this part. Okay, if K is taken as negative 1, so negative, there is U in W. This is the R2, W in R2. Okay, now let K become negative. So it means that KU is on the opposite direction. So this become the vector of KU. So since KU is not in R2, it's not in the space 2 dimension here, it's on the outside the R2 dimension. So KU is not in R2. Okay, since not in R2, so we say W is a subset of R2. Therefore, W is not a subspace. Okay, another example. Okay, another example. So all vectors, let's say W is all vectors in this form. Okay, in this form, which is first element of vector W. First component is real numbers and second and third component is 0. Okay, having this component in vector W. So we want to check whether W is a subspace or not a subspace. Okay, so let U become A00, V become B00, and U plus V is A plus B 0, 0. So we still have the same type of W. Okay, having first component is real numbers, second and third component is 0. So this one is a still uh, still set of W, and CU, when C times U is CA 0, 0, and this one is also still still set of or vectors in W. So therefore, since first and second condition match, we say that all vectors of the form A00, which is W, are a subspace of R3. Okay, all vectors of the form A00, which is W, are subspace of R3. Okay, this is how we show whether the vectors are the subspace or not a subspace by checking first and second criteria, are they met or not met. Okay, B. Okay, check whether the vectors of form A11, B11 are subspace or not a subspace. Okay, first condition U plus V, A plus B, 2 and 2. This is not in the form of A11 or B11. Okay, for CU, it's become CA, C and C. So this is not of the type of vectors of the form A11 or B11. So therefore, all vectors of the form A11 not subspace of R3. Okay, another example. Okay, check whether U and V of this type is subspace or not a subspace. Okay, let U become A plus C and C. In R3, V become a vector B plus D and D in R3. Okay, so if U plus V, so we having the addition of component like this. So we have the first component A plus B, second component C plus D, and the third component C plus D, and second component is A plus B plus C plus D. Okay, so this is still in the form of first and second component. Okay, still in the form of first and second component, whereby first second component is first plus third component makes second component, same as this one. First plus third component make second component. Same also goes for this V. Okay, so it met the first criteria. So for second criteria, KU, so it become KA plus C, and KC. So KA, third is KC, and second one is KA plus KC. So the second component makes from first plus third component. So it met the first and also second criteria. So therefore, all vectors of the form of U and V here are subspace of R3. Okay, next 5.3 is linear combination. Okay, what is linear combination? A vector V is a linear combination of vector V1, V2 until Vk if it can be expressed in the form of V equals C1 plus V1 plus C1 V1 plus C2 V2 plus until Ck Vk. So we call that V is a linear combination of V1, V2 until Vk, where C1 until Ck are scalar, which are called coefficient of the linear combination. Okay. Okay, example. Vector in R3 are linear combinations of I, J, okay, on every vector V, A, B, C in R3 is expressible as a linear combination, of the standard basis vectors I, J, and K. Okay, vectors in R3 are a linear combination of I, J, and K. Okay, it's supposed to be I, J, and K. Okay, I is unit vector, I a standard unit vector, which is 1, 0, 0. J is 0, 1, 0, and K is 0, 0, 1. Okay, since V is any vector in R3, so we can write as if V is ABC, where ABC is linear real numbers. So we can write A 1, 0, 0 plus B 0, 1, 0 plus Z 0, 0, 1. So this is V1. So this is J, and this is K. So I, J, K. So this is like V1, V2, and V3. So I, J, K can be written in the form of linear combination. Can be written as a linear combination for any vector in R3. Okay. Alright, so it means that standard unit vector, any vector in R3 can be written as a linear combination of standard unit vector I, J, and K in R3. Okay. Okay, another example. Consider vector U given by 1, 2, minus 1, and V given by 4, 6, 4, 2 in 3 dimension in R3. Now show that W 9 to 7 is a linear combination of U and V, and that W prime, which is 4, minus 1, and 8, is not a linear combination of U and V. Okay, now solution. Okay, in order for W to be a linear combination of U and V, there must be scalars K1 and K2 such that W can be written in the form of K1U plus K2V. If UV is a linear combination of W, so all vector in U and V can be written in the form of W equal to K1U plus K2V. So 9 to 7 here, W can be written as K1U K1U plus K2V. K2V. Or 9 to 7 can be written in the form, so we multiply in the scalar K1 and K2, so we have this one. Okay, so now we try to equate the corresponding component in I, J and K. So 9 is K1 plus 6K2, 2 is 2K1 plus 4K2, and 7 is minus K1 plus 2K2, this one. So we have this three equations, so we try to solve this. Solve using matrix. So you can use matrix to solve this to find what is K1 and K2. So we've got answer. K1 is minus 3 and K2 is 2. So you can solve using matrix. Okay, so K1 and K2 is given by minus 3 and 2. So therefore, W can be written, put back in here, K1 and K2. So W can be written as negative 3U plus 2V. Okay, so U and V can be written in the linear combination of W. Same also goes for W prime. W prime also, we use the same step as this one. Okay, so you can find W prime in the form of K1U plus K2V. Okay, so you can try out this one. Find what is K1 and K2 for this linear combination. Okay. Okay, if you are able to get the value for K1 and K2, then we say that it is a linear combination. If you are not able to find what is K1 and K2, therefore we say that W prime is not a linear combination of U and V. So it means that you try to find whether there is a solution for this. For the system of equation for this equation, whether you get answer for K1 and K2. Okay, continue from that one. So from 4 minus 1 and 8, we write in the combination of K1 U1 plus K2 U2 V2, K1U plus K2V, having this one. So equating the corresponding component, we have this set of equations. So this system of equation is inconsistent. Check back what is inconsistent mean for matrix. So no such scalar K1 and K2 exist. So it means that there is no solution for this one. So therefore, W prime is not a linear combination of U and V. Okay. Okay, next is 5.4 is spanning set. What is spanning set? If S is a set of all vectors V1 until Vk, set of vector in space N, then the set of all linear combination. Okay, set of all linear combination of V1 until Vk denoted by span S is called the subset of Rn. Span or generated by V1 until Vk. That is, span S is the collection of all vectors that can be written in the form of C1 plus C2 V2 plus until Ck Vk. Okay. Okay, example. Okay, example, determine whether V1 112, V2 101, and V3 211, V3 213, 313, span the vector space R3. Okay, solution. We must determine whether vector B, B1, B2, B3 in R3 can be expressed as a linear combination, like B equal to K1 V1 plus K2 V2 plus K3 V3. Okay, now let B1, B2, B3 in B. We can write in a linear combination of K1 V1 plus K2 V2 plus K3 V3. So therefore, B1, B2, B3 can be written in this form. Okay, now write in the form of system of equation like this. Okay, so this system is consistent. Okay, check back what does consistent mean to solve the system of equation in matrix. Okay, for all, it's consistent for all B1, B2 and B3 if and only if the coefficient matrix A, the coefficient of this one, coefficient of this, has a non-zero determinant. Okay, so only we have a solution only if the coefficient matrix here has a non-zero determinant. Okay, check whether it has a non-zero determinant or do not have a non-zero determinant. If it has a non-zero determinant, check its determinants. Then it can then the vector v1, v2, and v3 span the vector space R3.